notes for AP Calculus on the topic of improper integrals with infinite limits continued. So this one, we're going to evaluate each definite integral if it converges or show that it diverges. Okay? So some of these converge to a specific value, some diverge and don't converge to a specific value. So let's start with this one. Notice we got an upper limit of infinity. When you integrate cosine, that gives you sine, and since sine doesn't start with a c, it's positive, not negative. And then this is evaluated from 0 to infinity. And you can just change that to the brackets there to make it a little more user-friendly. And then you substitute the upper limit, infinity, minus the lower limit of 0. Well, sine of 0, that one's easy to evaluate, that's just 0. But sine of infinity, the easiest way to probably think about this is just thinking about the graph of sine as it heads off to infinity. Well, the graph of sine fluctuates back and forth between 1 and negative 1. Starts here at 0 and then goes, we're going off to positive, but to 1, then to negative 1. Back to 1, back to negative 1, and it keeps doing this forever as we head off to infinity this way. So that means sine of infinity also is just going to fluctuate between 1 and negative 1. So it never settles on a specific number, okay? It goes up to 1, then to 0, then to negative 1, then to 0, then to 1, then to 0, and it keeps going back and forth like that. Meanwhile, this part's just 0. So this one actually diverges, but it's a different reason than when we normally think of diverging as being infinite. This one is not infinite. It doesn't go to infinity, but it also doesn't settle on a specific value. It just keeps going back and forth between 1 and negative 1. So it also is considered divergent, or diverges, but for a different reason. It's not infinite, it's just never settles on a specific value because it goes back and forth between 1 and negative 1. All right, let's take a look at the next one here. So this one we've got x e to the negative 3x. You could try u substitution, setting u equal to negative 3x. But in this case, notice the derivative of that would be negative 3. And we'd still have this x out here. So we'd still have x e to the u. So u substitution wouldn't work on this one. So this one's actually going to require a method that we went over earlier in the year. Remember, integration by parts. So I'll write down the formula here, but you can also look back in your notes in Chapter 2, Sections H and I, is when we went over integration by parts. So the formula for integration by parts, remember you have to set one part of the integral equal to f of x, and one part of the integral equal to g prime of x. And then remember, it comes from the product rule, so it has the same components of the product rule, they're just in a different order here. What that equals is the original function, f of x times g of x, minus integral of the ones you find are the derivative of f of x, f prime of x, and then you find the integral of g prime of x, g of x. And for integration by parts to work, this should end up being simpler. This integral here, this part's already integrated. That's why it's called by parts. Part of it we've integrated, part of it we still have to integrate. This integral here should be simpler than what we started with. All right, so for this one, you just have to decide which part to set equal to f of x and which part to set equal to g prime of x. And there's no hard fast rule on which one to set equal to which, just some general guidelines. F of x, you want to be able to take the derivative, or it simplifies more by taking the derivative. G prime of x, you want to be able to integrate easily, or at least doesn't get much more complicated by integrating. So in this case, you can integrate and find the derivative of both of them, but the one that simplifies better by finding the derivative is x. And e to the negative 3x gets less complicated when you integrate, as opposed to x becomes x squared over 2 if you put it in. Worst case scenario, if you choose the wrong ones to start with, you can always discover that by when you get to this step, you'll discover the integral gets more complicated, and that's your clue. You probably assign them in the opposite of what they should have been. So here, f of x, or f prime of x then, the derivative of f prime of x would just be 1. And when you integrate g prime of x, you get g of x. That's where we can use the shortcut for u substitution. The e to the negative 3x part stays the same. And then the derivative of that would be negative 3. So instead of multiplying by negative 3 with the u substitution shortcut, remember you divide by, in this case, negative 3. So now we have everything we need to rewrite this with integration by parts. F of x is x. G prime of x, we just figured out, is e to the negative 3x over negative 3 minus integral f prime of x is 1, and g of x is e to the negative 3x over negative 3. So we can tell we assigned them correctly, because notice this integral is, look that much simpler, but it is simpler than the original one because it doesn't have the x inside there anymore. And this is what it would be if it was an indefinite integral. Difference is, this is a definite integral from 1 to infinity. So this one would be 1 to infinity, and this is the part that's already integrated, would be from 1 to infinity. So let's go ahead and simplify this one here. You could, to make it a little easier before substituting, you could pull out the negative 3 on the number, it's negative 1/3. And then all that's going to be left is x times e to the negative 3x. From 1 to infinity. Then over here, to make this a little simpler, you can pull out the negative 1/3, but it's already times the negative that's on the outside. That's part of the formula for integration by parts. So that makes it positive 1/3. And then integral from 1 to infinity of just e to the negative 3x, which is simpler again than the original one, something we can integrate there. And let's keep working out this integral, and then we'll substitute everything in at once. So we've got 1/3 on the outside. And when you integrate e to the negative 3x, again, you can use the shortcut for u substitution. You can just make that e to the negative 3x stays the same, divided by the derivative of negative 3x would be negative 3. It's just a constant, so you can use the shortcut. From 1 to infinity. Again, you can pull out the negative 1/3 times the 1/3 gives you negative 1/9. And then we're just left with e to the negative 3x. So now it's just a matter of evaluating. We can substitute infinity into this one, so we have negative 1/3 on the outside. And then we've got infinity here for the x times e to the negative 3 infinity minus, substitute 1 for x and then e to the negative 3. And then minus 1/9 on this one. Substitute infinity, so e to the negative 3 times infinity. Minus, when you substitute 1, it's just e to the negative 3. And then to simplify it further, let's let's rewrite the negative exponents so they're easier to analyze here. Here the infinity would just stay on the numerator here in orange. And this would move to the denominator, be over e to the 3 times infinity minus 1 over e cubed and then over here minus 1/9, and then rewrite each of these. 1 over e to the 3 times infinity minus 1 over e cubed So here, to analyze this one, infinity over 3 infinity. Well, they're both infinite, so you just have to remember which one grows faster. Polynomial one, this is like infinity to the first, versus an exponential one, infinity is up in the exponent. And remember, as you head off to infinity, eventually this exponential one, as long as the base is larger than 1, which it is here, e is about 2.7, ends up being much larger than the numerator. And so much larger that the numerator is basically negligible, so you have infinity on the denominator, which means this is going to be 0. So all that's left is the negative 1/3 times the negative 1 over e cubed. It gives you positive 1 over 3e cubed. And then something similar here, 1 over, this one's a little more obvious, 1 over this huge number, e to the 3 times infinity. That's 0, so all that's left is negative 1/9 times negative 1 over e cubed gives you positive 1 over 9 e cubed. Oops. So again, if this was free response, once you get down to pure numbers like this, you could stop right there. But multiple choice, they'd probably combine those to be a single fraction. By just multiplying this one by 3 over 3, you get a common number. So that would give you 3 over 9e cubed plus 1 over 9e cubed. Now the common number, you can combine those to be 4 over 9e cubed. So we got a specific number, so this one converges, and that's what it converges to. All right, let's take a look. A couple more here. This one, again, you can think use substitution, setting u to the denominator, but notice the derivative would be 2x plus 5, and there's no 2x plus 5 here to cancel out, so u substitution wouldn't work here. So if you can factor the denominator into 2 factors, like we can here, factors of 4 that add up to be 5 would be 1 and 4, so you can write x plus 1 times x plus 4. Then this is, remember, we can use integration by partial fractions. Or sometimes it's referred to as decomposition of fractions. And this one, you can look back at your notes. We originally went over this in Chapter 2, Section E, if you want to see some more examples of these kinds. So, remember, what we try to do is to decompose it into 2 fractions that are easier to integrate. So we take this 6 over x plus 1 times x plus 4, and we try to decompose it or break it into 2 fractions, each of which has one of these denominators as the factors. So one of them is, you can just call it a over x plus 1, doesn't matter which one goes first, plus the other one, b over x plus 1. And then we try to solve for one of these constants a and b are going to equal. So the first thing you can do is multiply the whole equation to wipe out the fractions by the least common number, which in this case is our 2 factors, x plus 1 and x plus 4. So that reduces both of the denominators here, both of the factors, x plus 1 and x plus 4, both of the factors on the denominator. So all you're left with is 6 equals, here the x plus 1's reduce out, so you're just left with a times x plus 4 plus Here the x plus 4 is reduced out, so you're just left with b times x plus 1. And then to solve for a and b, we're strategic and we choose specific x values. So if we want to get the a's to eliminate, you can let x equal -4. Sometimes there's an x on this side also, but in this case it's just 6. So 6 equals. We chose -4 because that'll make this 0 and wipe out the 8's. So a -4 plus 4 plus -4 plus 1. So we end up getting 6 equal 0 times a, that's 0, and this is -3 times b, so -3b. So then when you divide by -3, 6 divided by 3, you get b equals -2. So now we know what b equals. So it's going to go on the numerator right there. And then to solve for a, in a similar fashion, you let x equal -1 to wipe out the b, so we can solve for a. So 6 would equal a times -1 plus 4 plus b -1 plus 1. This time you can see that 0 wipes out the b's, and we're left with 6 equals -1 plus 4, that's 3a. Then divide by 3, so a is going to equal +2. They're not always opposite values like this. This one just happens to be. They're not always integers either. This one just happens to be. Sometimes you get fractions for these. So now we can rewrite this integral because we know this 6 over x plus 1 x plus 4 equals these. It's two separate integrals. Since they're added, we can split it into 2 to make it easier to integrate. So the only difference from what we did earlier this year is now we have an infinite limit here. So 2 to the infinity. A, we figured out is +2. So 2 over x plus 1 dx plus, integral again from 2 to infinity. B was -2. So -2 over x plus 1. Right, so if we just pull out the 2 here, out in front, notice we're left with 1 over x plus 1. So similar to 1 over x, that integrates to be natural log. And we can use the shortcut for u substitution. Normally you would say u equal to x plus 1. Here it's even more of a shortcut than on the previous one when we had the derivative was a constant. Here the derivative is just 1, in which case, remember, you don't even need u substitution because the derivative of 1 is not going to affect it at all. So it'd just be natural log absolute value of x plus 1. And then again, this is a value that you can leave the 2 as a constant, that's it, from 2 to infinity. Here you can pull out the -2. And when you integrate 1 over, sorry, this is x plus 1, this was x plus 4, sorry about that. Looking at the wrong one there. So that was x plus 4 that b was in it. 1 over x plus 4, that would be natural log absolute value of x plus 4. Evaluated from 2 to infinity. And then substitute those in. So 2. And then when you plug in infinity, well, plus 1, just like we did with our limits to infinity, is negligible. When you add 1 to infinity, it's just infinity, so that would be natural log of infinity. Minus, when you substitute in 2, natural log of 3. Notice the absolute value signs are there because sometimes you get negative numbers and the absolute value changes to positive. Here we're not going to get any negative numbers though. And then -2. You plug in infinity. Again, the plus 4 is negligible when you plug in infinity. So it'd just be natural log of infinity minus natural log of 6. And then if we distribute out the 2's to simplify this, or the 2 and the -2 here, Then we'll get 2 natural log of infinity. Remember that it just goes on the outside, minus 2 natural log of 3, minus 2 natural log of infinity, plus 2 natural log of 6. Then you can see that normally if this had just been by itself 2 natural log of infinity, that would be infinite and this would diverge. But in this case, 2 natural log of infinity and negative 2 natural log of infinity, those are like terms they cancel out, so it ends up not being divergent because the infinities are gone now. And you could again leave it like this. This was free response, 2 natural log of 6 minus 2 natural log of 3. We're just down to pure numbers here. But again, on these, a lot of times these are multiple choice questions, in which case they would simplify it further. Using your log properties, there's a couple ways to do this. You can factor out of 2 is one way to do it. And then you'd be left with natural log of 6 minus natural log of 3, which when you divide, when you subtract 2 logs with the same base, but we can condense them by dividing. So it'd be 2 natural log of 6 divided by 3. The one that's positive goes on the numerator, one's negative goes on the numerator, and that's natural log of 2. So it could be written as 2 natural log of 2. Or they might even use the exponent property here at the end. Move the 2 up. 2 should be natural log of 2 squared, which is just natural log of 4. So they might write it this way or this way. Usually they condense it to a single log if possible. Or another way to get the same end result there, you could also use the exponent rule first, move those 2's up. So you'd have natural log of 6 squared is 36, minus natural log of 3 squared is 9, and then condense them by dividing, so natural log of 36 divided by 9, which again also is natural log of 4. So more than one way to get there, sometimes using the log properties. Alright, so that's with integration by partial fractions. Sometimes you need that on these improper intervals as well. And one more. This one we don't have to use partial fractions or just got 1 factor squared or parts. It just requires you to use substitution, just a little more complicated because we can't use the shortcut on this one. There's 2 possible things to say u equal to, either the entire denominator or the function inside. But the entire denominator would have a derivative that's too complicated. Would have the chain rule that wouldn't just have x cubed to cancel out. So if you just say u equal to, with the function inside, oops, x to the 4th, not u to the 4th. This is not one we can use the shortcut on though, because the derivative is not a constant. So first thing we'd have to do is convert our lower and upper limits. When you plug in infinity to the 4th plus 1. Well, the plus 1 is definitely negligible, and we might not even need the 4th, but just to be on the safe side, sometimes it might matter, so just leave it there for now. And when you substitute 1, 1 to the 4th is 1, plus 1 gives you 2. And then we just have x cubed over u squared. And then when you find the derivative, du dx, you get 4x cubed. So dx equals du over 4x cubed. And you can substitute that right in there for dx. Then you can see the x cubes reduce out, which is what we want. You can pull out the 1/4 as a constant out in front to make it simpler. And notice this one doesn't involve natural log, even though it's in the number, because it's not u to the first. It's only u when it's the first power that involves natural log when you're integrating. So you would just rewrite this from 2 to infinity to the 4th of u to the negative 2. I'll just use our power rule. So you've got 1/4 on the outside. When you integrate u to the negative 2, you get u to the negative 1 over negative 1. From 2 to infinity to the 4th. You can pull out the negative 1 times 1/4 gives you negative 1/4. And then what you're left with inside is just 1 over u. From 2 to infinity to the 4th. just substitute those in. So you get -1/4 and 1 over infinity to the 4th. So you can see in this case, even if you put infinity, you would end up with the same thing. But sometimes it doesn't matter, so it's better to be on the safe side, even though in this case it doesn't. And then substitute 2. So again, we can see 1 over this huge number, 1 over infinity 4th, that's 0. So all that's left is -1/4 times -1/2 gives you +1/8. So this one also converges to a specific value of 1/8. And that concludes the notes for AP Calculus on the topic of improper integrals with infinite limits continued.